Okay, so today we're going to start off with something a little bit different. I'm going to start off with a problem, and I'm going to go through this kind of by hand and get a sense of how you would actually work out a problem like this. So here's what we're going to do. We're going to find the formula for the right endpoint Riemann sum on a given interval. Then we're going to compute the area under the graph as a limit. Okay, and this is going to be the problem that we're going to do. We're going to do f of x equals x squared on the interval from 0 to 2. Okay, let's give this a shot. All right, so we're going to start off. Let me go ahead and rewrite that. It's going to be f of x equals x squared, and from 0 to 1. Okay, so I want a right endpoint Riemann sum. Okay, so I want R of n. Okay, so remember R of n, I'm going to write out the general formula so we've got it. J goes from 1 to n, and we're going to take f of a plus j delta x, and then every time we multiply by delta x. Okay, I could have put the delta x here, or I could have put it out front. It doesn't really matter. Okay, this term does not depend on j, so it can actually be in here, or it can be over here. Okay, so let's write it with our particular function. Our particular function is x squared, and our a is 0, and our b is 1. So I'm going to plug in. J goes from 1 to n, and our function again is x squared, and a is 0, so it's going to be 0 plus, and oh, I got to find delta x, so I'm going to put delta x up here. Delta x will be 1 minus 0 over n, so just 1 over n. That's a pretty easy one. So j remains in there, and I'm going to have delta x, which is 1 over n. That's squared. And delta x, again, this delta x that goes here, is 1 over n. Okay? So take a look at this again. F of a plus j delta x. Delta x is 1 over n. A is 0. Okay, j is j. Delta x is 1 over n. And the function is take the input and square it. Here's the input, square it. Okay? So that's the same thing. That's R of n. Now if I put in the number 6, that's going to be 6 subintervals. So I put in the number 2 for n, that's 2 subintervals. So that's all this is. I'm just making that a 1. Okay, so this problem said I want to go ahead and write a right endpoint Riemann sum, and then I want to look at what happens is I let the number of subintervals get infinitely large. That is, let them get infinitely large so that the size of each subinterval gets infinitely small, and we get a really, really nice approximation. Okay, so I want to take the limit of as n goes to infinity of R of n. This is going to get me a pretty gosh darn good approximation. So the limit as n goes to infinity of j going from 1 to n of, now 0 was just 0, so it's going to be j times 1 over n squared 1 over n. Okay, so I'm going to simplify this here before I take my limit. Okay, the limit as n goes to infinity. All right, let's simplify the sum part. I'm not going to deal with the limit just yet. I'm just going to start dealing with the sum part. Okay, now I can distribute this square through, so I end up with this. Keep the sum in there, j from 1 to n. Okay, I'm going to get j squared over n squared times 1 over n. Okay, well, I'll simplify that. Limit again as n goes to infinity of sigma j from 1 to n, and I have j squared over n cubed. Alright, now let's just take a look. Again, forget about the limit part for a second. Let's just look at the sum part. So I'm going to rewrite it down here. I'm going to just put the limit just so I know that it's actually there, but we don't have to worry about it just yet. We'll deal with that last. Notice that all we care about is, does this thing depend on j? Doesn't matter if it depends on n. N is just a number, remember, but j is an index. So this number here, n, does not depend on j. So I can pull it out front. 1 over n cubed. J from 1 to n of j squared. Now, we have a formula that will help us find j squared. I have to look it up. Actually, I never remember it myself. So here I am looking it up. Okay, and the formula has a couple forms. I'll write it both ways. So the limit, again, as n goes to infinity. I still have the n over 3. Sorry, n over 3. The 1 over n cubed. And 1 to n, j going from n of j squared, simplifies it with a formula. And the formula is n times n plus 1 times 2n plus 1 all over 6. All right, well, this is getting interesting now. Now I have, as n goes to infinity, the limit of a rational function. And one of the forms of this, I can simplify this as n cubed over 3 plus n squared over 2 plus n over 6. Almost there. I'm going to distribute. I'm going to get the n cubes go away. I get 1/3 plus. Okay, n squared over n cubed 2, so it's going to be 1 over 2n plus 1 over 6n squared. Good. Now let's evaluate the limit as n goes to infinity. This just goes to 1/3 because 1/3 doesn't have an n in it. This, as n goes to infinity, this goes to 0. As n goes to infinity, this also goes to 0. So our limit, as n goes to infinity, is 1/3. That means the exact area underneath x squared from 0 to 1 is exactly 1/3. Okay, so that's the. This is a fairly detailed, fairly difficult problem. I must admit. I'm only going to give you a couple problems like this. Okay, I'm going to expect that you are able to do a very simple one, something like f of x equals x or f of x equals x squared. But this is not a big focus. So we'll practice a couple in class. Again, I wanted you to see what one of these looked like, where we actually write out the Riemann sum, okay, the right endpoint Riemann sum, and then we take the limit. Okay, this is why we're learning all these j squared business. Okay, so copy this one down. We'll be practicing these more in class. Okay, so we got that one. That's all set. We're computing the area under the graph as a limit.